Okay. Thank you for the introduction. I hope you're all seeing my slides now. Okay. So I will be talking about this bisimilarity for diagrams. And my talk will mostly be in two parts. I would like to start by introducing this general framework to think about bisimilarity, which is not coalgebra, and then instantiate it in the case of diagrams and see what we can do with it. So let me start with this categorical framework of open morphisms. So I guess most of you are more familiar with this coalgebraic framework for bisimilarity. And this talk is not about coalgebra, it's about a framework I like to call a lifting approach for bisimilarity, where systems are basically modeled by some object in a category. And all you need to do is to specify a subcategory of this category of system, which is called the category of paths, that basically model the kind of runs you want to consider in your systems. And much as the coalgebraic case, you can describe bisimulations and bisimilarity as span of morphisms that have some sort of properties. And in this case, it's some lifting properties. So I will talk a lot about transition systems in this talk. So I want to make sure everyone is using the same kind of transition system. So for me, a transition system is those labeled transition system with an initial state. And we can make them into a category by considering those functions between states that preserve the initial state and the transitions. I will also talk a lot about bisimulation, and particularly those strong bisimulations, which are just those relations between states that relate the initial states and that have this back and forth property. That is, if you can make a transition in one system, you can mimic this transition in the other system. The first observation is that the morphism of transition system induces a simulation. That is, a bisimulation without this third condition, this symmetric condition. In a sense that the graph of a morphism is a simulation. And a natural question is, how can we get bisimulation using morphism? And for example, what are the morphisms whose graph is a bisimulation? And depending on the framework you are using, the answer will be slightly different. But in this talk, I want to show that the morphism with some lifting properties, precisely the lift transitions, is the morphism that we are looking for. So I've been using the word lifting a lot in this talk, and it's probably time I describe what I mean precisely, because it's different from what Daniela has been talking about previously. And it's another standard notion in category theory that a morphism F has the right lifting property with respect to G, if only if every time you have such a plane commutative square between F and G, you have a diagonal that makes the two triangles commute. And the morphism we are looking for which the graph is a bisimulation, are precisely those morphisms which have the right lifting property with respect to all the branch extensions. And a branch extension is just an inclusion of a finite linear system into a longer finite linear system. And the key observation is that two systems are bisimilar if only if there is a span or morphism between them. So let me take some time in showing an example of a right lifting property in this context of transition system. So let's try to prove that this morphism F has the right lifting property with respect to this extension. And by this extension, I mean including this branch of length 2 to a branch of length 4. And by this morphism F, I mean the quotient that identify those two states. So we want to consider all those commutative squares between f and x. And actually, we don't have much choice. The only choice is to map this AB to this AB, and this ABAA to this ABAA. And the commutativity of the diagram means that if you look at the image of AB, then you obtain AB in this system, and the ABAA you picked here is actually just an extension of the AB from the image. And the question becomes, do we have a diagonal here? That is, can we extend this AB into ABAA here, such that the image is ABAA here? And the answer is yes, just insert it like this. So like this, we prove that F has the right lifting property with respect to X. However, F is not an open map because if we change ABAA into ABAB here, we want to extend AB so that the image is ABAB. And you can see that you will be blocked here because you don't have any B transition. So now I can abstract away everything I've been talking about in transition systems in what is called a categorical model, which is just a category M that you can think as a category of systems, together with a category P of paths. So in the case of transition system, M is precisely the category of transition system, and P is the subcategory of branches and branch extensions. And I can abstract away the notion of P openness, which is just those morphisms that have the right lifting property with respect to all the morphisms in P. And the notion of bisimilarity becomes the existence of a span of open morphism between two objects. And P bisimilarity, this notion of bisimilarity, can actually model many notions of known bisimilarity. And in particular, when your notion of bisimilarity behave well with some notion of runs, typically if you have history-dependent notions, then very probably you can model it with P bisimilarity. So Joyal, Nistel, and Vinsker in their first paper about open bisimilarity, path bisimilarity, introduce some relational kind of characterization of P bisimilarity. But the key observation is that since P bisimilarity is a notion on runs, not really on states, those relations must be relation on runs and not on states. So it's not too much of a problem for transition systems because you can always translate a bisimulation into a relation between runs like this by just basically relating two runs if all the intermediate states are related by the bisimulation. And you obtain a relation between runs that have those kind of properties. So the first three ones are basically the same as strong, the condition of strong bisimulations. And the last one is just saying that if you have two runs that are related, then restricting those runs to some prefix, then those prefix must be related. And it's easy to see that bisimilarity is equivalent to the existence of such a relation between runs. And that's what can be abstracted away for any categorical model, assuming that the category of path is a small category. So again, a bisimulation will be a relation between execution. And in this context, for example, an execution of X is just a morphism from a path to X. So you will relate an execution in X with an execution in Y. And this relation is required to have a bunch of properties, so which are the same properties as here. Actually, they have two notions of bisimulations, depending on whether you require the last property of restricting the runs. And if you require it, you obtain a strong path bisimulation. If you don't, you obtain a path bisimulation. In particular, they prove that those bisimilarity are related in this way. But actually, those implications are not equivalent in general. A few years ago, we proved that we have a general framework that contains already some interesting examples for which the first implication is an equivalence. And also the case of transition system is a bit particular because all those three notions are equivalent and correspond to strong bisimilarity. Okay, so now that I have introduced this general framework to do bisimilarity, I want to instantiate it in the case of diagrams. And what I mean by a diagram is the standard notion of diagram in category theory. That is, you fix a category, and a diagram is just a functor from a small category to your fixed category. And my interpretation is that the domain of the diagram in some sort of category of runs, the fixed category is some sort of category of observation, and the diagram maps every run to the observation you see during the run and how these observations evolve during execution. We can make those diagrams into a category whose morphism are those pair of functor relating the domains of the diagrams and some natural isomorphism that basically said that if you send an object of C into an object of D, then you must require that they have the same observation, which is given by this isomorphism. You may be wondering why I'm interested in diagrams and some notion of bisimilarity for diagrams. And that actually comes from directed algebraic topology that I've been studying during my thesis, where from a topological space with some ordering structure, we wanted to construct some algebraic invariants for those spaces. And it turned out that diagrams with values in some modules or vector spaces are a nice invariant for those spaces. And it also turned out that this back and forth property of a bisimilarity is a very interesting way of comparing those diagrams. And especially the view as an open morphism were very interesting to prove that things were bisimilar. So that's where it comes from. Another nice thing about diagram is that we can encode all categorical model into diagrams. So for example, if you take a transition system, you can encode it as a diagram in an easy way. The domain of the diagram is just the poset of all its runs ordered by prefix. The observations are given by some words ordered by prefix. And the diagram just maps a run to its label. And this construction can be made more general for any categorical model. That is, given an object of a category of systems, you can define the domain as, again, a category of runs, whose objects are those morphisms from a path to your system. And the observation is given by the shape of the execution itself, and the diagram maps a run to its shape. We can prove that this extends actually to a functor from the categorical model to the associated category of diagrams. And when the category is co-complete, we have a left adjoint to this functor, which is given by just co-limiting those diagrams. And it turns out that the associated comonad is just given by the unfolding, if you take the case of transition system, for example. And we could prove that in many cases, in particular in the case of transition system, the co-unit is actually an open morphism, which means that theoretically we can prove that the unfolding is bisimilar to the system, and actually in a very strong way. So now I have these diagrams that have some interesting directed algebraic topology, and for which we can encode all those categorical model. And I told you I want a bisimilarity definition for those diagrams. And I want to use this theory of open maps. So the only thing I need to do is to define a category of paths. And this category of paths is actually very simple and very similar to the case of transition systems, which are given by those branches and branch extensions. A branch is, again, a finite linear diagram, and the branch extension is just including a finite linear diagram into a longer finite linear diagram. And we can define bisimilarity as the existence of a span of open morphism. That is, those morphisms that have the right lifting property with respect to branch extensions. If we come back to this adjection between a categorical model and a category of diagrams, we can prove that actually this functor pi preserve open morphisms. That is, if you have an open morphism in your categorical model, then the associated morphism of diagram is open for this notion of openness. And in particular, it means that two systems are bisimilar, implies that the diagrams are bisimilar. And I will show you a bit later that the converse is not true, and I will explain why precisely. Okay, so now that we have bisimilarity for diagrams, we naturally want to have bisimulations for them. So I told you that we had those path bisimulations every time you have a categorical model, but I told you that those work only when the path category is small. And in the case of diagram, this almost never happens when your category of observation is not small. And in particular, I want to consider a diagram with value in vector spaces. So we cannot have this property. So we need to design our own bisimulations for this notion of bisimilarity. Again, the interpretation will be quite similar to path bisimulation. It will be some sort of relation between runs. More precisely, it's a relation between objects of the domain of F and the objects of the domain of G. But remember that in my interpretation, an object of the domain is just a run in your system. So basically, a bisimulation is the relation between runs. And we require, again, this back and forth property, which is described here. But remember also that we want that when two objects are related, then they have the same observation. And this is given by an additional component in this relation, which is a witness that the two observations are the same, which is an isomorphism in the category of observation. And in the back and forth property, we add this witness in such a way that this witnessing is natural in the categorical way. And of course, the nice property is that two diagrams are bisimilar if only if there is a bisimilation between them. So the first use of bisimilation is that we can start looking at decidability of bisimilarity. And I try to convey that in the definition of bisimilation, there are two components: the relation part, the relation between the objects, and the isomorphism part. And for decidability, we need to restrict to some finite diagrams, that is, diagrams whose domain is finite. So in a way, by limiting to finite diagrams, it means that the relation part is kind of trivial. You can just guess the relation, and you can just reduce yourself to a problem of isomorphism in the category of observation. So for example, in the case of diagrams with value in vector spaces, we can reduce to a problem of finding some invertible matrices that have some linear relation between them. You may argue that limiting to finite diagram is not very reasonable, especially if you think about the transition system case. The thing is, it's an important case in directed algebraic topology, because when we have some kind of finitely presented spaces, we can actually compute some finite diagrams. So that's already important to be able to decide whether those diagrams are bisimilar or not. And in this paper, I gave some decidability results. And maybe the main one is the case of diagrams with value in real and rational vector spaces, which is one of the main cases we are interested in. And I told you that this problem can be reduced to a problem of invertible matrices. And this can itself be reduced to a problem of polynomial equations in reals, which is known to be decidable by quantifier elimination. Another use of bisimulation is to close our comparison between bisimilarity in categorical models and bisimilarity in diagrams. So I told you that bisimilarity in categorical model implies bisimilarity in diagrams, but not in the other way around. And actually, we can prove this key observation that bisimulations between diagrams induced by systems are precisely up to some encoding to pass bisimulations between the system, which means that the bisimilarity of the induced diagrams corresponds to pass bisimilarity and not p bisimilarity. You may be wondering if we can actually capture strong pass bisimilarity, that is adding this restriction condition on the pass bisimulations. And the answer is yes. It's just obtained by extending the diagrams, adding additional information. So basically, those diagrams just look at how the observation evolved by extending the runs. And in those other diagrams, we look at how the observation evolved by extending the runs and also restricting the runs. And we can make the whole same theory and prove that for those extended diagrams, bisimilarity corresponds to strong pass bisimilarity of the systems. I think I'm a bit early, but that's basically what I wanted to talk about today. So thank you for your attention.
Thank you very much for your talk. Yeah, I would like to ask, we still have time for questions. Are there questions on the chat? I don't see questions, but maybe you can speak up orally. Anyone? If not, I have a question. Can you, right, you mentioned it here at the bottom of the conclusion slide, what is left open. So what do you plan to do next in this line of research? Can you say something about future work?
Yeah, so the from a directed algebraic topology point of view, I'm really interested in the case of diagrams with value in abelian groups. Because basically we are doing homology, if you know a bit about algebraic topology. And homology can be with values in real vector space or into abelian groups. And in abelian groups, we have much more information. So if we are able to decide bisimilarity of diagrams in abelian groups, we'll be a bit more happy. But the problem is we cannot do the same kind of proof technique to reduce to the theory of reals, because the theory of integers is not decidable. So we have to be more clever to do something. That's
this is interesting. So can you say something about the finite exponent case in the case of abelian groups? Can you do you have an algorithm there?
What do you mean precisely about finite?
I mean, the abelian groups, I mean, they are sort of classified, right?
Yeah, sure.
And so I was wondering if it's like direct sums of finite field, like Z2 to the omega times like a finite exponent abelian groups, where there's no integers showing up.
So just basically, okay, so if just, how to say?
Like the most basic example of such a group would be two-element group to the infinite dimensional.
So probably it should be decidable, because I think the theory of finite field is decidable. So probably the same kind of proof technique would work, if I'm guessing. I'm not entirely sure, but that's my guess. But as
so it's rather about the integers which causes problems here. Yeah?
Yes, basically, yes.
Okay, so other questions? We still have time. Yeah, please, Uli.
Yes. So you have this other work where you are relating bisimilarity using open maps to co-algebraic bisimilarity. Co-algebraic. Is there a version of this which extends to this work on diagrams?
So basically, the relation we were working on is from coalgebra to open maps.
Yep.
So yeah, I don't know exactly in which direction would you like to extend it.
Yeah, me neither. I'm sorry.
But there is a work in the other way, from open maps to coalgebra. But this work required the path category to be small. So it doesn't work with diagrams.
Yeah, okay, yes, yeah.
So there might be something to do in this direction.
Okay, thank you.